Today we will discuss projection operators. What do you mean by a projection operator? Let us define. Let X be a linear space and P be a linear operator on X. Then P is said to be a projection operator if and only if P square is equal to P. That is, P is an idempotent. Clearly, null operator and identity operator are projection operators. We note that if P is a projection operator on a Hilbert space H and M is the range space of P, then any element in M is of the form, any element Y in M is of the form Px, where X belongs to H. And we note that image of Y under P is equal to P of Px is equal to P square X, because P is a projection operator. So P square is equal to P. So we have Px and Px is nothing but Y. So we note that image of any element of the range space is the element itself. That is, if Y belongs to P, then Py is equal to Y. Now we shall prove a theorem. Let P be a bounded projection operator on a complex Hilbert space H with range space M and null space N. Then M is orthogonal to N if and only if P is self-adjoint. Let us prove this theorem. First, we shall show that H is the direct sum of M and N, where M is range space of P and N is the null space of P. For X belongs to H, Px belongs to H because P is a mapping from H to H. And so X minus Px also belongs to H because H is a linear space. And P image of X minus Px is equal to Px minus P square X, since P is linear. And this is equal to Px minus Px because P square is equal to P, as P is a projection operator and Px minus Px is 0. So we find that image of X minus Px under P is 0. That means X minus Px belongs to the null space N of P. So X minus Px belongs to M. And for X belongs to H, Px always belongs to M range space. And we can write X is equal to Px plus X minus Px. That is, we have written X as the sum of an element of M and an element of N. And since X is any element of H, so any element of H can be written as sum of an element of M and an element of N. That is, H is the linear sum of M and N. Next, we have to show that M intersection N is singleton 0. 0 here, 0 is null vector. As M and N are subspaces of H, so 0 vector belongs to M and 0 vector also belongs to N, and so 0 vector belongs to M intersection N. If possible, there exists some non-zero element X in M intersection N, then X belongs to M and X belongs to N. X belongs to M implies there exists some Y in H such that Py is equal to X, since M is the range space. And if Py is equal to X, then Px is equal to P of Y, because X is equal to Py, and this is equal to P square Y. And since P is a projection operator, so this is equal to Py and Py is equal to X. So we find that if X belongs to Pm, then Px is equal to X. And X belongs to N implies Px is equal to 0. So we find Px is equal to x and Px is equal to 0. But every element has the unique image, and so this is not possible, or we can say that x must be equal to 0, which is a contradiction because we have assumed that x is a non-zero element in M intersection n. Thus, M intersection n is equal to singleton 0. So earlier we have shown that H is the direct sum, H is the linear sum of M and M intersection n contains only 0 vector. So H is the direct sum of M and N. And now we have to show that if M is orthogonal to N, then P is self-adjoint. So let us prove this. So let M is orthogonal to N. That means every element of M is orthogonal to every element of N. That means inner product of xy is equal to 0 for every x belongs to M and for every y belongs to M. And we have to show that P is self-adjoint, that is P star is equal to P. Let Z belongs to H, and since Z is direct sum of M and N, so every element of Z can be uniquely written as sum of an element of M and an element of N. So there exists some X in M and Y in N such that Z is equal to X plus Y. And inner product of P star Z and Z is equal to P's inner product P star, and replace Z by X plus Y, and we have this. And by the definition of Hilbert adjoint operator of P, as P is a bounded linear operator, so its Hilbert adjoint operator exists, and so we have inner product x plus y, P of x plus y. And since P is linear, here we can write Px plus Py. And since y belongs to N, so Py is equal to 0. And since x belongs to M, and from the earlier remark, Px must be equal to x. So we have inner product x plus y and x. And by the definition of inner product, we have inner product x and x plus inner product yx. And then we have this is equal to inner product x and x plus 0. Here y belongs to N and x belongs to M, so their inner product is 0. And then here 0 can be replaced by inner product of x and y because this inner product is also 0. So we can write here x inner product xn plus inner product xy. And by the definition of inner product, we can write here inner product x plus y. And earlier we have seen that P of x plus y is equal to x. So here x can be written as P of x plus y and x plus y. And then replacing x plus y by z, we have inner product Pz and z. Here z is any arbitrary point of H. So this condition holds for any z belongs to H. So we have this. And this implies that inner product of P star z and z minus inner product Pz and z is equal to 0 for every z belongs to H. And then we can write here inner product by the definition of inner product P star z minus Pz and z is equal to 0. Then this can be written as inner product of P star minus P of z and z is equal to 0 for every z belongs to H. And since H is a complex Hilbert space, so here operator must be equal to null operator. So P star minus P is equal to null operator. And this implies that P star is equal to P, that is P is self-adjoint. Conversely, suppose P is self-adjoint, then we have to prove that M and N are orthogonal. For each x belongs to M and for each y belongs to N, inner product of xy is equal to inner product pxy. From the earlier remark, x belongs to N implies px is equal to x. So here x can be replaced by px. And since by definition of Hilbert adjoint operator, we can write inner product x p star y. And since p is self-adjoint, p star is equal to p, so we can write inner product x p y. But y belongs to the null space N, so py is equal to 0. And inner product of x and 0 is 0. And so we find that for every x in M, for every y in N, inner product of x and y is equal to 0. So every element of M is orthogonal to every element of N. That is, M is orthogonal to N. Thank you.